Welcome to the AI Coach by Anil Nathu. It is truly a pleasure to have you join us for a deep dive today. Now, if you're anything like us, you're constantly grappling with the exhilarating, almost dizzying pace of artificial intelligence. It feels like every single day there's a new breakthrough, a new application, a new concept emerging, shaping our world at, well, an unprecedented speed. It's hard to keep up, isn't it?
It absolutely is, yeah. The sheer volume of cutting-edge research papers and industrial patents being churned out globally is truly staggering. It's just this vast ocean of information. And for any one individual researcher or even a large organization, tracking how those, raw scientific breakthroughs actually transform into tangible, real-world technological applications it feels like an impossible task sometimes. That crucial connection, that vital bridge, often gets completely lost in the sheer volume and complexity. It just vanishes.
And that's precisely why we're taking a deep dive into something genuinely revolutionary today, something really different. We're exploring a brand new data set and its incredibly ingenious methodology, specifically designed to, cut through that noise. Our mission, our singular goal, is to help you understand how this monumental effort maps the entire AI innovation journey, giving us all a much-needed shortcut to being truly well-informed about AI. Finally.
Exactly. We're unpacking a meticulously crafted paper titled DeepInnovation.AI, a global data set mapping the AI innovation and technology transfer from academic research to industrial patents. And this is far from just some, abstract academic exercise. It represents a colossal undertaking by a team of visionary researchers: Hexing Gong, Wei Zhu, Xingzhu Liang, Xiwen Meng, Pinlong Kai, Xingcheng Zhu, and Jinjing Kuei. Their work isn't just about collecting data. It's poised to revolutionize how we perceive, understand, and frankly interact with the entire AI landscape. It's big.
The core promise of Deep Innovation AI is bold, really bold. It asserts itself as the first comprehensive global dataset to truly bridge that crucial, often disconnected gap between academic research papers and industrial patents. Think of it, if you will, as the Rosetta Stone for AI innovation, finally translating that pure scientific discovery into its practical, real-world applied form.
It's a fundamental game changer for anyone navigating the AI landscape. It really is. Throughout this deep dive, we'll explore the critical challenges this data set was built to overcome. Then we'll peel back the layers to understand the ingenious methodology behind its creation, which notably includes the cutting-edge application of advanced AI models like GPT-4 and BERT. Very current stuff. And most importantly, we'll uncover the profound insights it unlocks for anyone invested in the future of AI. From anticipating global trends to identifying emerging areas for collaboration, this deep dive offers a robust foundation for understanding AI innovation dynamics and technology transfer processes. It's very much in line with the practical, data-driven guidance you'd expect from the AI Coach by Anil Nathu.
Okay, so let's start by really unpacking this urgent need for deep innovation insight. First, the AI landscape itself. It's not just expanding, it's exploding, right? Playing an absolutely pivotal role in the global innovation ecosystem. We're talking about a field that's not merely growing, but driving economic transformation and intensifying technological competition on a scale we've rarely, if ever, seen before. It's huge.
Oh, absolutely. The raw numbers really drive this point home with, undeniable force. The global AI market isn't merely on an upward trajectory. It's projected to reach an astounding $826.7 billion by 2030. Just think about that number. That's not just growth. It's a monumental surge, with a compound annual growth rate projected at 28.46% from 2024. To put that into perspective, this isn't just a market trend. It's a fundamental sweeping shift in the global economy. Kind of like the Industrial Revolution or the dawn of the Internet age, it's truly transformative.
Wow. And you can vividly see this explosion mirrored in the patent landscape too, can't you? The World Intellectual Property Organization, the WIPO, which is essentially the global body overseeing patents and intellectual property. They've reported that AI-related patent applications worldwide have just surged dramatically. They've exceeded a 30% annual growth rate every single year between 2014 and 2023. That's nearly a decade of explosive growth. This incredible pace of patenting isn't just a sign of ideas proliferating. It signals that these ideas being formalized, legally protected, and rigorously prepared for market application. It's a clear indication of accelerating technological innovation and concrete industrial progress. Things are moving fast.
And what's truly fascinating here is the distinct yet deeply interconnected relationship between academic papers and patents. The sort of yin and yang of innovation, if you like. Academic papers are where the cutting-edge scientific breakthroughs are initially documented. The pioneering algorithms, the theoretical advancements, the foundational discoveries that push the boundaries of knowledge, that's the science bit. Patents, on the other hand, reflect the tangible technological applications, how those discoveries are engineered into practical solutions, new products, innovative services, the how-to bit. Analyzing these two disparate yet complementary sources together provides a uniquely clear, almost X-ray-like picture of how knowledge truly evolves. You really see the whole flow. It reveals regional strengths in innovation, illuminates global competitive trends, and maps out the entire journey from, say, a research lab bench to the bustling global marketplace.
But, and this is a significant but, isn't it? There's this inherent data dilemma. Why has this kind of comprehensive innovation tracking, this holistic view, been so incredibly hard to achieve until now? The visionary authors of the Deep Innovation AI paper, Haixin Gong and Jinjing Kuo, alongside their dedicated team, they meticulously identified 3 significant limitations that existing data infrastructures consistently face. And understanding these deeply ingrained challenges is absolutely crucial before we can truly appreciate the monumental scope and impact of their solution. You need to know the problem first.
Exactly. The first major limitation they pinpointed is fragmentation. It's a huge issue. Current databases, as impressive as they might seem in isolation, fundamentally operate in silos. They just don't talk to each other. You have highly specialized academic platforms like Google Scholar or Dimensions, brilliant for unearthing research articles, great stuff. Then, entirely separately, you have dedicated patent databases like Google Patents or Derwent Innovation, focusing purely on technological implementations and legal protection. Also great, but separate. This inherent separation creates a significant disconnection. It means that most historical research has analyzed papers or patents independently, making it incredibly difficult, almost impossible, to directly connect a theoretical advance, say, a new neural network architecture, to its subsequent practical application in a patented device. This fragmentation severely hinders efforts to observe the full continuous innovation process. You just see pieces.
Right. It's like trying to understand an entire symphony by only listening to the brass section or only reading the sheet music for the strings. You get pieces, isolated brilliance maybe, but you completely miss the grand interactive performance, the seamless interplay between the theory and its applied realization. You miss the whole picture.
Precisely. The second limitation they addressed is incomplete coverage. This is another big one. Existing systems frequently suffer from severe restrictions in geographic scope and timeliness, which severely hinders any attempt at truly global comparative analyses. You just can't compare like for like globally. For instance, much of the historical patent research often focused exclusively on single jurisdictions, like USPTO patents in the United States. Important, but limited. Even broader platforms, while expansive, often lack the specialized AI classification systems that are absolutely essential for a truly granular, in-depth analysis of AI-specific innovations. Furthermore, inherent language differences and inconsistent technical classification standards across various countries further complicate any efforts to make robust cross-regional comparisons of innovation. It's like trying to compare apples and oranges when you only have half the fruit, some of it is in a different language, and you don't even have a consistent way to measure them. It's messy.
And then the third limitation, which in many ways is perhaps the most significant in terms of really understanding the quality and impact of innovation. That's insufficient evaluative capacity.
Yes, that's key. Current datasets typically lack robust quantitative measures of innovation quality. How do you objectively tell the difference between a mere incremental improvement, say a slightly faster processor, and a truly transformative breakthrough, like the invention of the transistor itself? How do you quantify that difference? How do you accurately assess competitive intensity between different companies or countries beyond just counting patents? It's not just about volume. Without these objective quantitative metrics, understanding the full spectrum of AI innovation dynamics, its true pace, its underlying direction, its profound impact becomes virtually impossible. This was a critical, almost insurmountable gap. And it's exactly the kind of challenge the AI Coach by Anil Nathu focuses on helping people overcome by providing insights that are truly data-driven and actionable, not just surface level.
Okay, so that brings us directly to the evolution of text analysis itself. This seems absolutely central to how deep innovation AI successfully addresses these complex challenges. Historically, researchers relied on what you called keyword dictionaries, right?
That's right.
Yeah, that sounds pretty straightforward. You just manually search for terms like artificial intelligence or machine learning within documents. Sounds easy.
True, it was easy to implement, but it's also incredibly limited in its utility. Really quite basic. This method fundamentally neglects contextual nuances. A single word can mean wildly different things depending on its surrounding context within a sentence, And crucially, for a rapidly evolving dynamic field like AI, These fixed keyword lists simply cannot keep pace with the rapid, almost daily emergence of new terminology. Think about how concepts like diffusion models or large language models have exploded onto the scene and become central to AI discussions in just the last few years. A static keyword list would miss that entirely. You'd end up with a significant underestimation of innovation.
Right. The Deep Innovation AI paper itself gives a perfect real-world example of these keyword limitations. They point to a study by Dimioli et al. From 2024, where they use only about 50 predefined keywords to identify AI patents. And while that was maybe a solid starting point back then, that approach risks significantly underestimating the true extent of AI innovation today, potentially missing a vast array of recent advances in areas that don't neatly fit those 50 terms, like cutting-edge NLP or novel generative AI architectures that might use entirely new jargon. You just miss them.
Exactly. That's precisely where the new frontier comes in. Advanced machine learning, particularly deep learning methods for natural language processing, or NLP, a truly pivotal development that completely revolutionized text analysis was BERT bidirectional encoder representations from transformers.
BERT. Okay, it still sounds like something from a sci-fi movie, but how exactly did it transform text analysis in a way those old keyword lists couldn't? What's the magic?
Well, its revolutionary power lies in its ability to understand the context of words, not just from what came before them, but equally from what comes after. This bidirectional understanding is key. It means it excels at classifying texts with vastly greater accuracy and semantic depth, even across multiple languages, because it truly grasps the nuanced meaning of words based on their surrounding context. It moves far beyond just simple keyword matching. It understands the intent and relationships within the text. It gets the meaning.
But even with BERT's significant advancements, were there still challenges when it came to applying it to large-scale innovation research? It wasn't perfect yet?
No, not quite. Despite its undeniable power, current studies utilizing BERT for innovation research often relied on relatively small, often curated datasets, like lab experiments. These simply weren't truly representative of the vast fragmented global innovation landscape. Also, much of the previous work focused on proving BERT's effectiveness in controlled academic settings, rather than applying it to analyze the sheer scale of millions of papers and patents worldwide. So, as the authors Hasting Gong and Jingjing Quan note, there was a significant lack of thorough evidence of BERT's effectiveness when scaled up to analyze millions of papers and patents worldwide. This was a major hurdle for truly comprehensive global innovation studies. Scaling it up was the challenge.
And that, ladies and gentlemen, is precisely where Hasing Gong, Jingjing Quan, and their co-authors step in with Deep Innovation AI. This is where the true game changers come into play. It's a comprehensive, integrated dataset meticulously designed specifically to analyze global AI technology innovation and transfer, directly addressing all those profound limitations we've just discussed.
Their first major contribution is the development of an advanced multilingual text processing system. This isn't just one technique, it's a remarkably sophisticated blend, a hybrid approach. It intelligently combines keyword matching for initial rapid screening, then leverages the raw power of large language models like GPT-4 for deeper, nuanced semantic understanding, and finally employs dual-layer BERT classifiers for highly accurate, fine-grained identification and classification of AI-related content. This multi-layered synergistic approach ensures unprecedented precision and scalability. It's like using multiple tools for the job.
And the scale truly is unprecedented. This is their second monumental contribution. Deep Innovation AI is unequivocally the most extensive data set of its kind ever assembled. Seriously impressive. We're talking about an incredible 3,511,929 academic papers and 2,356,204 patent records. Just staggering numbers. And this isn't just a fleeting snapshot. It meticulously covers over 60 years of data, systematically drawing from all major AI innovation countries and regions globally. That kind of historical depth and global scope is absolutely vital for constructing a truly complete and accurate picture of AI innovation. You need that long view.
Totally agree. Their third pivotal contribution lies in quantifying knowledge transfer. This is where they definitively bridge that long-standing gap between theory and application. They do this by calculating the textual similarity between academic research papers and industrial patents. How close are they, really? Using specialized, cutting-edge tools like KeyBERT for intelligent keyword extraction and Doc2Vec for deep, document-level semantic understanding. They meticulously construct a cosine similarity matrix. This matrix precisely quantifies the direct knowledge transfer between fundamental academic research and its subsequent industrial application. enabling a precise, measurable understanding of AI innovation diffusion patterns. It literally shows you, with data, which papers are directly influencing which patents. It draws the lines.
Wow. And finally, their fourth, truly groundbreaking contribution, the measurement of novelty through hypergraph analysis. This is incredibly fascinating because it moves far beyond traditional citation metrics, doesn't it?
Way beyond. Instead of merely counting how often a paper or patent is cited, which, while useful, is a retrospective measure of past impact looking backwards, they've developed a method to measure the statistical rarity of knowledge combinations. How unusual is this mix of ideas? This innovative approach allows them to objectively identify truly technological breakthroughs and accurately assess competitive dynamics based on how genuinely unique and unexpected a new innovation is. This is incredibly powerful for identifying what's genuinely new and disruptive, rather than just what's popular or getting cited a lot. It spots the real leaps.
That's a huge difference. So putting it all together.
Taken together, these advancements unequivocally position DeepInnovation.AI as an invaluable, indeed indispensable resource. It really is. It offers academic communities, industrial innovators, and policymakers a far broader, more nuanced, and dynamic view of global AI technology innovation. It supports deeper data-driven insights into its evolution and profound impact, providing precisely the kind of comprehensive, actionable intelligence that powers the AI coach by Anil Nathu.
Okay, we've covered the why, the urgent need for this type of insight. We've laid out the problem. Now let's really dive into the how. How did Haixin Gong and Jingjing Kuai and their team actually construct this groundbreaking data set? We're now going to peel back the layers and really dig into the ingenious methodology behind DeepInnovation.AI. Let's get into the mechanics.
Right. The foundational framework they meticulously built upon is elegantly simple in concept, but immensely powerful in execution. Data integration quantitative evaluation network mapping. That's the core structure. This framework is the logical scaffolding for their entire approach. It's designed to comprehensively study the entire innovation process, viewed as a continuous pipeline, from scientific discovery in the lab through technological invention as ideas take shape, and finally to industrial application as those inventions are commercialized. Seeing the whole journey, this holistic end-to-end view is precisely what fundamentally sets DeepInnovation.AI apart from any prior efforts. It's not just a collection of data points, it's a structured pipeline built specifically for understanding the full life cycle of innovation.
And the sheer scale of this integrated approach is, frankly, mind-boggling, just the numbers involved. The dataset, after all the processing, contains 6.42 million structured records globally, spanning an impressive time frame from 1960 all the way to 2020. That's 60 years. That includes the 3.5 million academic papers and 2.3 million patents we discussed. But what's truly astonishing, and must have been computationally intensive, is that it also maps approximately 100 million paper patent pairs. That's the sheer volume of connections they've painstakingly identified and quantified.
Yeah, the computational load is immense. To achieve this colossal feat, the research framework is architected upon three main interconnected modules. Think of it in three parts. Module 1 is text acquisition and classification, which acts as the sophisticated engine for accurately identifying and categorizing AI documents, ultimately generating the core DeepPatentAI and DeepDiveAI datasets. Module 2 is hypergraph-driven innovation quantification, which serves as the intellectual brain calculating the elusive yet crucial metric of patent and paper novelty. How new is it? And finally, Module 3, the paper-patent similarity, functions as the vital bridge, meticulously connecting foundational research to practical application by precisely measuring their semantic associations, connecting the dots.
Okay, let's start with Module 1, Smarter AI Identification. This is where Haixin Gong and his team truly grappled with the messy, complex reality of accurately classifying AI patents on a global scale. What were the specific hurdles they had to overcome there?
They faced several deeply ingrained challenges. One significant hurdle was multilingual semantic ambiguity. Languages are tricky. Non-English texts, especially highly technical ones, are notoriously difficult because a direct, literal translation often misses the nuanced implied meaning, particularly with rapidly emerging or highly specialized AI terms. Words change meaning fast. Another key challenge was dynamic technological boundaries. AI is an incredibly fast-evolving field, as we said. Concepts like diffusion models, which are now central to image generation, might not have even existed or been widely recognized just a few years ago. Fixed classifications get outdated really quickly. And finally, annotation noise. Patent claims, by their very legal nature, sometimes employ strategically ambiguous expressions designed to maximize protection. This inherent noise makes precise, automated classification notoriously difficult. They're written carefully, maybe vaguely on purpose.
So to tackle these multifaceted challenges, they developed a truly sophisticated hierarchical framework that they term a coarse screening, fine screening verification process, like a funnel. This ingenious approach integrates initial keyword matching, then leverages the power of large language model, LLM inference, and finally employs those dual-layer BERT classifiers we touched on earlier. It's a multi-stage approach designed for getting AI content identified with unparalleled precision.
Exactly. Let's break down this meticulous process step by step. The first stage is data acquisition and initial filtering. Where did they get the raw data? Their colossal starting point was the Intelligent Innovation Dataset, or IEs, a massive collection of nearly 100 million patent records. Huge. This dataset itself was the result of a remarkable collaboration between Fudan University, Bo1 Innovation, Shanghai Big Data Technology Co., Ltd., and Shanghai Artificial Intelligence Laboratory, demonstrating the power of academic-industry partnership right there. For their AI classification, they focused specifically on patent titles and abstracts, recognizing that these sections, while concise, typically contain the essential text for identifying a patent's AI relevance. Get the core idea.
Okay, and to get that initial coarse screen, that first wide net, they created an AI keywords and international patent classification IPC relationship table. This table intelligently combined established standards from WIPO's Patent Scope AI Index and China's CNAPA. So they effectively used authoritative recognized classification systems to perform a preliminary sorting of patents into AI or non-AI. It's a smart way to efficiently filter a massive volume of data right from the start, isn't it?
Absolutely. A very clever first pass. Once they had that initial course classification, the next and very innovative step was LLM annotation, which brought in the formidable power of GPT-4. To efficiently and accurately analyze these pre-filtered documents for AI relevance, they leveraged OpenAI's GPT-4 model, renowned for its exceptional semantic understanding and robust performance on vast datasets. The process itself was quite streamlined. First, they combined a carefully designed prompt, essentially a set of instructions, with the patent text, title, and abstract. Second, they submitted this combined input to GPT-4. And third, the model provided a straightforward true or false decision, indicating whether the patent was AI-related or not. Yes or no.
That's a truly clever way to automate high-level intelligence at scale. Can you give us a sense of what that prompt looked like? How did they guide GPT-4 to be so precise in its AI classification? What did they tell it?
Yeah, the prompt was designed with exceptional specificity to minimize ambiguity. It's quite detailed. It instructed GPT-4 directly. You are an artificial intelligence AI patent classifier. Tells it its job. Your task is to determine whether each provided text consisting of a patent title and abstract is related to AI. Focus on identifying AI-related topics such as machine learning, deep learning, neural networks, natural language processing, computer vision, and other core AI technologies or applications. This level of detailed instruction was absolutely crucial, ensuring that the annotations generated by GPT-4 were highly precise and consistently relevant. It kept it focused. These annotations, in turn, produced the critical initial labeled samples needed for the subsequent, even more refined, stages of classification. This whole approach truly exemplifies the kind of intelligent automation that the AI coach by Anil Nathu often highlights, using AI itself to accelerate insights and decision-making in complex data environments.
Right, so those precisely labeled samples then fed into the next critical step, hierarchical classifier construction, which is where the dual-layer BERT system truly comes into its own.
Yeah.
Why 2 layers, though? Why not just one incredibly powerful, all-encompassing BERT model? Wouldn't that be simpler?
Well, the dual-layer architecture consisting of BERTutor and BERTner was meticulously designed for paramount accuracy and robustness. It's about reliability. This staged approach allowed them to efficiently filter and categorize patent data with increasing levels of precision, like refining the results. BERTutor, acting as the initial coarser classifier, was built using GPT-4's highly reliable initial reviews and then trained on a carefully selected small sample set of 60,000 patents, specifically 30,000 AI patents and 30,000 non-AI patents. This established the foundational broader classification, acting as a first pass filter, get rid of the obvious non-AI stuff.
Okay, and then BERTner, the fine-grained classifier, took that initial classification and refined it to an even higher degree of precision, like zooming in.
Exactly. BERTner was trained on a much larger and more robust dataset. a total of 1 million samples. That's a lot of data to learn from. This impressive set included 500,000 high-confidence AI patents that were initially identified and annotated by GPT-4, alongside 500,000 representative non-AI patents that had been rigorously selected by BERT, a balanced diet for the model. These million samples were then robustly split into 80% for training, 10% for validation, and 10% for testing. Standard practice, but essential. This multi-layer stage system ensures extraordinarily high-quality AI classification by progressively refining the categories, moving from a broad initial sweep to an incredibly precise and accurate identification of AI content. It just gets better and better.
And finally, to ensure that this entire intricate system was working as intended and producing reliable results, they performed rigorous dataset validation. You have to check your work, right?
Oh, absolutely. That final validation step was critical. They systematically evaluated the performance of BERT using a separate, completely unseen test set. How does it do on new stuff? And crucially, they also benchmarked its performance against an independent, meticulously manually annotated evaluation set of 6,000 entries, compared it against human experts. This comprehensive, multi-pronged approach, integrating domain-specific terminology mapping, a dual-layer classification architecture, and deep semantic analysis, effectively addressed the inherent complex challenges of classifying massive, large-scale global patent data with incredibly high accuracy. And the results speak for themselves. The model achieved a remarkable 0.975 accuracy on its machine-generated test set, and a still impressive 0.908 accuracy on the manually annotated set, unequivocally demonstrating its strong generalization capabilities. It works really well. This performance significantly outperformed previous deep learning and traditional keyword-based methods, truly setting a new standard.
Wow, that's an incredibly thorough and impressive methodological achievement. Really solid work. Let's move on to Module 2. Quantifying innovation with hypergraph-driven novelty. You mentioned earlier that traditional citation metrics, while useful in their own right, don't truly capture the essence of novelty. Can you elaborate on that limitation for us again? Why aren't citations enough?
Of course. Traditional citation-based metrics primarily track impact retrospectively. Looking back, a paper or patent that's cited a lot is certainly impactful, demonstrating influence, sure, but that doesn't necessarily mean it introduced a fundamentally new idea. It might simply be a very good synthesis, an efficient application, or a highly accessible explanation of existing knowledge. Popularity isn't the same as novelty. These metrics, by their nature, fail to capture the surprising, often unexpected combinations of ideas that are the true hallmarks of transformative discoveries. They miss the sparks. They tell you what was popular, but not necessarily what was genuinely novel.
So it's not just about how many people referenced it, but about how new and unique the underlying idea or combination of ideas actually is. That's the key difference.
Precisely. This is where the theoretical bedrock of their work comes in, building on the insightful research of Shi and Evans from 2023. Their work demonstrated that truly unexpected configurations of knowledge elements, those combinations that are least predictable based on existing patterns and historical connections, are surprisingly strong predictors of outsized scientific impact and future breakthroughs. The weird combinations are often the best ones. Think of it like a master chef. Traditional methods might just tell you how many times flour or sugar appear in recipes, basic stuff. But hypergraph analysis in this context looks at the unique and surprising combinations of ingredients, the unexpected pairing of, say, flour, sugar, and saffron when no one else thought to combine them in that particular way, to create an entirely new, exquisite dish. It's about measuring the unexpectedness that leads to true innovation, finding the secret ingredients.
That's a fantastic analogy. It really helps visualize it. So, how does Deep Innovation AI actually calculate this novelty using this hypergraph approach? What's the process?
It's a clear multi-step computational process. First, the BERT model, which we touched on earlier, extracts the key technological features from patent texts, like pulling out the main ingredients. Think of BERT as a smart summarizer that identifies the most important conceptual terms or phrases, providing a structured, concise summary of the patent's core knowledge. Second, sophisticated deep learning techniques then meticulously analyze the complex, intricate relationships between these extracted technological elements. How do these ingredients usually combine? They're looking for patterns, or rather, the absence of expected patterns, looking for the surprises. Third, a numerical novelty indicator is calculated for each patent by cleverly combining hypergraph theory with probabilistic models, giving it a score.
And what does that calculation actually mean conceptually for us without getting bogged down in the deep math? What does a higher novelty score tell me? What's the takeaway?
Conceptually, it models the innovation degree by treating each patent as a unique combination of various technological elements. a recipe, basically. A higher value signifies greater novelty because it directly reflects the statistical rarity, the unexpectedness of that particular knowledge combination within the vast existing body of patents. How unusual is this recipe? It's an objective way to identify whether a patent truly combines existing concepts in a way that hasn't been widely seen before, or at least is highly unusual in the current body of knowledge. This is a true game changer for identifying genuine breakthroughs, not just incremental improvements, and helps forecast which innovations are most likely to have transformative impact, spotting the next big thing.
Okay, that makes so much more sense now. I can really visualize that unexpected recipe concept much clearer. Now for Module 3. Connecting the dots, paper patent similarity. This module seems to be where that Rosetta Stone aspect of deep innovation AI truly shines, allowing us to see the direct lineage from research to application. This is the bridge, right?
It absolutely is. This particular study introduces the first global matrix explicitly linking AI-related academic papers to patents, a huge first. This is a monumental achievement because it quantitatively maps the direct, tangible connection between foundational academic research and its eventual technological innovations, all on a global scale. It's the vital bridge that makes the entire, often opaque innovation journey transparent and visible, revealing how scientific concepts migrate into patented solutions. You can actually see the flow.
And how do they achieve this incredibly complex semantic connection across millions of documents? That sounds computationally heavy.
It is. They employ a robust, multi-step framework designed for deep semantic understanding. First, for semantic feature extraction, they utilize KeyBERT again, this time to pull out key technological terms from both scholarly articles and patent texts, creating a unified initial feature space, finding the common language. Then, they applied Doc2Vec, a powerful model specifically designed to map entire documents into a high-dimensional vector space, effectively capturing deep, document-level semantic information. So, imagine each research paper and each patent becoming a unique fingerprint or point in this vast conceptual semantic landscape, placing them on a map of ideas.
And then they use those fingerprints or points to calculate cosine similarity. Can you explain what that means in simple, intuitive terms for our listeners? How does that work?
Sure. Think of cosine similarity as a sophisticated measure of how similar two documents are, not by their exact words, but by their underlying meaning, their core ideas. If you imagine those fingerprints as vectors in a multi-dimensional space, cosine similarity measures the angle between them. Are they pointing the same way? If the angle's very small, meaning the vectors point in roughly the same direction, the documents are semantically very similar. They're talking about very closely related ideas, close together on the map. If the angle's large, they're far apart, their meanings are dissimilar, different topics. It's a remarkably powerful way to quantify, with a numerical score, how closely related the ideas in a specific academic paper are to the ideas in a specific patent.
Okay, got it. Like measuring the distance between ideas.
Yeah.
And this rigorous process then leads to the association matrix construction, building the network.
Correct. Using these precisely computed similarity scores, Haixingong and Jinjinhua and their team built a bipartite network which essentially links individual papers to individual patents based on their semantic similarity, drawing the connections. Now, due to the sheer computational and storage constraints of trying to calculate every single possible association between 3.5 million papers and 2.3 million patents, which would literally be trillions of pairs, it's just too much, they very intelligently implemented this methodology on a highly representative subset of 10,000 papers and patents as a robust proof of concept, a smart sample. This allows researchers to identify significant knowledge transfer pathways, and the excellent news is that the authors have made their code publicly available. They shared it. So researchers with sufficient computational resources can extend this approach using the deep innovation AI data to investigate specific technology transfer cases if they wish. You can build on their work. This is another area where having guidance, perhaps like that from the AI Coach by Anil Nathu, can help you understand how to leverage these complex tools and data relationships for practical innovation insights in your own work.
Excellent. So we've thoroughly covered the why this data set is needed and the incredibly detailed how they built it. We've seen the engine. Now let's get to the most exciting part for our listeners, the what. What does this deep innovation AI data set actually reveal when it's put into action? What kind of profound insights can you truly gain from leveraging it? This is where deep innovation AI really comes to life. What can you do with it?
Right. The first thing to emphasize, which is a massive win for the entire global research and innovation community, is access. It's open. The Deep Innovation AI dataset, thanks to the commitment of Hexing Gong, Hui Zhu, Xingzu Liang, Xuan Meng, Pinlong Kai, Xingcheng Xu, and Jingjing Hua, is publicly available on Figshare. This transparency is fantastic for accelerating research and innovation worldwide. It's not locked behind a proprietary paywall. Anyone can get it.
That's a huge step towards democratizing AI knowledge.
Yeah.
Fantastic news. And it comes in a thoughtfully designed modular structure, right? Making it relatively easy to use.
Exactly. It's organized into 3 primary CSV files, each serving a distinct purpose. Makes it manageable. First, there's DeepPatentAI.csv, which contains those 2.3 million patent records. Each record is rich with 8 key attributes, like the patent ID, unique patent number, the IPC code, title, abstract, year, keywords, and that crucial calculated novelty score we discussed, all the patent info. Second, DeepDiveAI.csv encompasses the 3.5 million academic papers, each with 13 metadata fields, including ID, title, source, abstract, author names, publication year, cited count, keywords, language, type, affiliations, and its own calculated novelty score, all the paper info. And finally, DeepCosineAI.csv, which is the heart of the connectivity, containing approximately 100 million calculated paper-patent similarity pairs based on those precise cosine similarity calculations we explored at the connections file.
So to summarize, this is an incredibly comprehensive collection. It meticulously documents global AI research and technological innovation from 1960 to 2020. Linking academic literature and patent documents with these innovative quantitative indicators. It's essentially an entire interconnected AI innovation ecosystem mapped out with data, a huge map.
Precisely. And this data set isn't just a static collection of raw data points. It is fundamentally a powerful, dynamic lens for deep analysis. You can ask questions of it. It revolutionizes how we can conduct comprehensive innovation analysis across multiple critical dimensions. This is exactly the kind of deep, actionable insight that the AI Coach by Anil Matthew aims to help you apply directly to real-world challenges, whether you're a policymaker, an industry leader, or an investor, making the data useful.
Okay, let's look at the first compelling application, understanding the global AI competition network structure. What fascinating insights does Deep Innovation AI reveal about the worldwide AI race? Who's winning?
Well, by analyzing keywords, international patent classification, IPC codes, which inherently embed geographic information about where a patent was filed, and the sophisticated semantic vectors derived from the DeepPatentAI.csv file, researchers can meticulously map out the intricate global AI competition landscape, see who's connected to whom. What's consistently and starkly revealed is a clear core-periphery hierarchical structure. Some are in the center, many are on the edges. The key finding here is that the United States and China unequivocally occupied dominant positions at the very core of this global network. They are the big players, while a vast majority of other countries were being relegated to the periphery, demonstrating comparatively limited technological development and interconnectedness. It's not just that US and China lead, but how isolated some others appear in the network.
Wow. So if you're a policymaker in a country aspiring to AI leadership, or maybe a business leader contemplating global expansion, what concrete insights does this core periphery finding provide for you? What does it mean practically?
This data is invaluable, really powerful. The connection density and strength within this network serve as robust indicators of both technological complementarity, who works well together, and competitive intensity between countries who's fighting for the same space. For national policymakers, this information is absolutely crucial for shaping national AI innovation policies. For example, understanding precisely where to invest to either accelerate catch-up or alternatively, where to strategically specialize in niche areas of AI development to create competitive advantage. Play to your strengths. For corporations, it directly guides strategies for international market entry or the formation of strategic partnerships, clearly showing where potential collaborators are strongest, or conversely, where competitors might be weakest or where a significant innovation gap exists. Find the opportunities. Ultimately, it helps optimize the allocation of scarce resources in AI at a macro level, ensuring that investments are made where they can yield the most significant strategic advantage and impact. Put your money where it counts.
Makes sense. Next, let's look at AI technology theme analysis. This sounds like dissecting the AI field to understand its distinct areas of focus. What can we truly learn about the differing priorities within AI research versus application?
Exactly. The Deep Innovation AI dataset enables a comprehensive and granular analysis of AI technology themes through the structured terminology found within the keywords field of both DeepPatentAI.csv and DeepDiveAI.csv, looking at the words they use. What emerges as truly fascinating and insightful is a clear divergence in focus between academic and industrial innovation. They talk about different things. Patent documents, by their very nature, typically emphasize applications and practical implementation. How do you use it? You'll see keywords like methods or how neural networks are being specifically used for a particular task, or image processing integrated into a commercial product. Real-world stuff. Academic papers, on the other hand, consistently focus more on fundamental theories and abstract concepts, such as deep learning as a core principle, rather than its immediate specific application. The underlying ideas.
That distinction makes perfect intuitive sense. The research lab is typically exploring the fundamental principles and pushing theoretical boundaries, while industry is figuring out how to build something practical and valuable with those principles. That fits. What specific insights does this divergence offer to our listeners, whether they're in academia, industry, or investing? How can you use this?
Well, such detailed theme analyses facilitate the precise identification of technological frontiers, what's genuinely emerging in basic academic research versus what's currently being broadly applied, refined, and commercialized in industry, what's new versus what's being used. For businesses, this provides empirical foundations for critical innovation strategy decisions. Should they be investing heavily in fundamental long-term core research, or should their focus be on more immediate applied development and product refinement? Where should they bet? For a research institution, this analysis can highlight areas where their theoretical work is most likely to find strong industrial application, or where there are significant research gaps that industry desperately needs filled. Where's the demand? It helps both sides bridge the infamous valley of death between discovery and commercialization, ensuring research aligns with market needs and vice versa, making connections happen.
Very useful.
Yeah.
Then there's AI spatiotemporal evolution analysis. This sounds like tracing AI's complex journey not just through time, but also across various geographies around the globe, tracking the spread.
Indeed. Researchers can meticulously track how AI technologies evolve and diffuse across both time and geography by combining the year, novelty scores, and IPC, International Patent Classification information, derived from both the DeepPatentAI and DeepDiveAI datasets, putting all on a timeline and map. The key findings from this analysis are profoundly illuminating. First, there's a clear and undeniable exponential growth in overall AI activities. We're simply seeing more research, more patents, more everything at an accelerating rate. It's just taking off. However, and this is truly crucial for strategic planning, there's a notable divergence in innovation patterns, a split. While patent innovation, meaning the creation of new applied technologies, continues to grow steadily, almost linearly, academic paper innovation shows a declining trend in novelty. That's interesting.
A declining trend in novelty for academic papers. That sounds counterintuitive, almost alarming for such a fast-moving and seemingly innovative field. What exactly does that mean? Is it a bad sign? Should we be worried?
Not necessarily negative, no. And this is where the nuance of deep innovation AI's insights becomes so valuable. It's subtle. It potentially indicates the maturation and standardization of core research paradigms within academia. The field might be growing up. Essentially, the foundational, truly paradigm-shifting discoveries in academic AI might have largely been made or solidified in prior decades. The big breakthroughs might be behind us, for now. Now the overwhelming focus is shifting to application, refinement, optimization, and building upon those established foundations, making things better, not necessarily brand new. It's less about discovering a brand new fundamental law of AI and more about making existing AI work better, faster, more efficiently, and for new problems. Engineering versus pure science. It's a sign of a maturing field where the focus moves from what's possible to how do we make it work effectively and reliably. And, of course, the geographic analysis within this framework consistently highlights significant global imbalances in innovation, unequivocally reinforcing the core periphery observation with the United States and China emerging as the predominant leaders in the field. That pattern holds.
Okay, that makes sense. It's a shift in focus. So, for our listeners, what are the actionable insights that this spatiotemporal analytical framework can provide? What should you take away?
It offers invaluable insights for tracking specific technological development trajectories and assessing their maturity. Is this tech new or old news? For investors, this data helps identify if a company they're considering is working on a truly novel, groundbreaking breakthrough that could redefine a market versus simply optimizing an existing mature technology. Where is the real disruption? For policy advisors, it allows them to critically assess the effectiveness of current innovation policies, are national investments truly yielding the intended results in terms of novelty and application, and to accurately forecast future technological trends, guiding where to strategically direct precious R&D funding for maximum long-term impact. Understanding this shift from foundational novelty to applied innovation is key for long-term strategic planning for anyone involved in AI. Know where the puck is going.
Absolutely. And finally, let's discuss AI knowledge transfer analysis. This really gets to the core of how abstract scientific knowledge becomes real-world tangible applications and drives economic value. Show me the money, right?
Well, it shows the pathway at least. This is truly fascinating because the paper-patent correlation matrix, housed within the DeepCosineAI.csv file, provides the precise quantitative foundation for examining this critical transformation, the connection data. This matrix meticulously measures knowledge transfer intensity from foundational research to industrial application through those sophisticated textual semantic similarity calculations. How strong is the link? Visualizations derived from this, such as Figure 8 in the paper, which showcases the 500 paper-patent combinations with the absolute highest similarity scores, starkly reveal key knowledge transfer pathways. You can literally trace which academic research is most directly and consistently leading to patented inventions, creating a visible bridge that was previously invisible, seeing the flow of ideas.
So researchers can adjust those similarity thresholds to fit their specific needs, right? They can zoom in or out. What kind of in-depth insights can you specifically gain from this granular level of analysis?
Exactly, you have flexibility. You can establish different similarity thresholds based on your specific research objectives. Want strong links or just related ideas? This allows you to analyze both the efficiency of knowledge transfer, how quickly and effectively discoveries move from academia to industry, and the time lag characteristics of scientific discoveries as they evolve into technological innovations. How fast do ideas travel? This precise approach helps identify the most effective knowledge transfer patterns, revealing what kind of research is most successfully making it to market. What works best? It also allows for a data-driven evaluation of the industrial returns on scientific research investments, which is crucial for funding bodies and universities. Are we getting value for money? This provides robust empirical evidence to support science and technology policy formulation and optimize innovation management strategies. This is incredibly powerful for anyone looking to invest in or build upon AI research, offering a level of clarity and foresight that was simply unavailable before for understanding the pipeline of innovation. It illuminates that crucial path.
That brings us to our final segment, practical lessons and future applications. Expert speaker, after exploring all this incredible work by Hixing Gong, Jingjing Kuai, and their colleagues, why does deep innovation AI truly matter to our listener? On a practical, actionable level, what's the bottom line?
The core overarching lesson from Deep Innovation AI is profoundly clear. To truly grasp the full scope and trajectory of AI, you must see the whole picture. You can't just look at one part. From the conceptual theories developed on the lab bench to the tangible applications formalized in the patent office, the whole journey, this integrated holistic view, which explicitly connects fundamental research to applied technology, is absolutely crucial for making genuinely informed strategic decisions in the incredibly dynamic AI space. You need both sides of the coin. It's about understanding the entire life cycle of an idea from start to finish.
So for the researchers and academics listening, what direct benefits does this data set offer them in their own work? How can they use it?
For them, Deep Innovation AI provides an unprecedented, almost real-time tool. It helps them identify emerging research gaps that the market needs filled. See where the demand is. They can track the real-world impact and uptake of their own work, see if anyone's noticing, and they can discover highly relevant potential industrial collaborators who could commercialize their discoveries. Find partners. It actively encourages interdisciplinary thinking and helps pinpoint precisely where fundamental theory is not just interesting, but truly ripe for practical, impactful application. Find the sweet spot. It helps ensure their groundbreaking work doesn't just stay confined to academic journals, but makes a real difference.
Makes sense. And for policymakers and government strategists who are tasked with guiding national competitiveness in AI, what's in it for them?
Well, Deep Innovation AI offers empirical, data-driven evidence to directly guide national AI strategies. Hard facts, not just guesswork. It provides a robust framework for assessing the effectiveness of existing innovation policies. Are investments actually yielding the intended results in terms of real-world AI innovation and competitive advantage? Is the strategy working? It also helps precisely identify areas for targeted investment and deeply understand global competitive dynamics, allowing a nation to strategically secure or enhance its position in the global AI race. Where to place the bets. For instance, understanding that core periphery dynamic between the US, China, and other countries helps immensely in allocating resources strategically, either to compete head-on or to find potent niche areas of strength. play smart.
Okay. What about industry leaders and innovators in the private sector? This seems like a gold mine for them, right?
It unequivocally is a goldmine for competitive intelligence and strategic R&D planning. Absolutely. Industry leaders can use this data to anticipate technological trends with much greater foresight, seeing what's truly coming down the pipeline from academic labs. Get ahead of the curve? They can identify potential licensing or acquisition opportunities by seeing which academic breakthroughs are most effectively translating into valuable patents, allowing them to acquire cutting-edge technology more efficiently. Smart shopping for tech. And critically, it helps them objectively assess the novelty of their own innovations against a global benchmark, ensuring they're not just reinventing the wheel, but truly focusing resources on breakthroughs. Are we really innovating? This aligns perfectly with the AI Coach by Anil Nathu philosophy of optimized learning and application, empowering businesses to make smarter, more strategic moves in the fast-paced AI landscape. Be strategic, not just busy.
And for investors, particularly those in venture capital or private equity, trying to spot the next big thing in AI, how does this help them?
For investors, the ability to precisely trace knowledge transfer pathways and quantitatively assess the true novelty of innovations allows for significantly more informed, de-risked investment decisions. Better betting. You can pinpoint areas where academic excellence is most effectively and rapidly translating into tangible commercial value, identifying high-potential ventures with a clear, verifiable lineage from groundbreaking research to market readiness. Find the real gems. This is about intelligent investing, moving beyond buzzwords to data-backed opportunity. Follow the data.
Absolutely. Ultimately, deep innovation AI represents a significant and truly transformative leap forward in our collective ability to understand, predict, and yes, even strategically steer the trajectory of AI innovation globally. It's a powerful new tool. It empowers stakeholders across various sectors with the precise, data-driven insights needed to make agile, impactful decisions in this rapidly evolving technological landscape.
Okay, so now let's wrap up with a practical action plan, something you can actually do. This is how you can begin to implement key learnings from this deep dive into the Deep Innovation AI dataset by Hexing Gong, Huizhu, Xingzhu Liang, Xiwan Meng, Penlong Kai, Xingcheng Zhu, and Jingjing Guo. This framework offers powerful new ways to understand the AI innovation ecosystem, and this plan is a testament to the practical guidance offered by the AI Coach by Anil Nathu, turning insight into action.
Okay, step one. We recommend you monitor AI innovation trajectories. Keep your finger on the pulse. Make it a regular practice to review major AI patent filings and academic publications in your specific domain and interest. Don't just read the news headlines. Critically, focus on identifying pairs of papers and patents that exhibit high semantic similarity, as revealed by the DeepCosineAI.csv concept. Look for those strong connections. The benefit here is clear. This helps you track in real time how specific scientific discoveries are translating into industrial applications, providing invaluable early signals of emerging technologies and potential disruptions before they hit mainstream awareness. See it coming.
Good advice. Second, assess innovation novelty. Think about how new your ideas really are. For any new projects or R&D initiatives you're contemplating, conceptually apply the novelty metric from Deep Innovation AI. Ask yourself, are we truly pursuing novel combinations of knowledge elements that could be transformative? Or are these merely incremental improvements on existing technologies? Be honest. The immense benefit is that this encourages a fundamental focus on breakthrough innovation rather than just minor advancements, driving your efforts towards truly impactful discoveries as quantified by the hypergraph analysis methodology. Aim high.
Third, analyze global competitive landscapes. Know who you're up against and where the opportunities lie. If you're involved in strategic planning, market entry, or even assessing international partnerships, conceptually map the core periphery structure of global AI competition. Draw your own map. Identify not only the dominant players like the US and China, but also the niche opportunities and underserved areas. Where can you fit in? This insight directly informs crucial decisions on international collaborations, strategic market positioning, and precisely where to allocate your resources to gain a sustainable competitive edge in the global AI arena. Play the global game smartly.
Fourth, align research with application. Bridge that gap we talked about. For academic researchers, this means proactively evaluating whether your theoretical work has clear, tangible potential pathways to industrial application, guided by the theme analysis that shows the divergence between academic and patent keywords. Think practical. For those in industry, it's about actively seeking out academic research that directly addresses your current or future application needs. Look for solutions in the labs. The profound benefit here is bridging the persistent theory-practice gap, optimizing the return on investment for both scientific discovery and technological development, ensuring research finds its way into practical use. Make the connection work.
And finally, fifth, forecast spatiotemporal trends. Look ahead, using the past and present as your guide. Keep a keen eye on the overall exponential growth of AI activities, as the data unequivocally shows. Things are still moving fast, but just as importantly, pay close attention to the nuanced divergence between patent innovation, which continues to show steady growth, and academic paper innovation, which might indicate a maturing field where foundational discoveries are giving way to applications. Understand the different speeds. This dual perspective is invaluable for long-term strategic planning, helping you understand where the field is maturing and where new foundational research or entirely new paradigms might still be desperately needed. Plan for the future state.
Excellent summary. We've truly navigated the intricate, fascinating world of AI innovation today, all thanks to the pioneering and meticulous work behind the DeepInnovation.AI dataset by Hsing Gong, Hui Zhu, Jingzhu Liang, Xuan Meng, Pinlun Kai, Xingcheng Zhu, and Jinjing Hua. It's really their achievement we've been discussing. This remarkable dataset and the advanced methodologies it employs offers an unparalleled lens for understanding the full, complex life cycle of AI technology, from initial scientific discovery right through to its industrial application. A powerful view.
So consider this as we close, a final thought for you. If we can now so precisely map the past and present of AI innovation with this unprecedented clarity, what profound ethical and strategic responsibilities does that place on each of us to wisely and intentionally guide its future? The ability to measure and predict innovation means we also have a greater power to influence it. More power means more responsibility, right?
Yeah.
What innovations will you foster? What bridges will you build now that you have a clearer, more data-rich map of the entire territory? What will you do with this knowledge?
That's a great question to leave our listeners with.
Thank you for joining us today. Visit the AI Coach website for more AI insights.